We will start with really measurements. So first off, when you do take measurements, it is really important to not only record a number, but you should always record units, right? Units are pretty much the most important part of any type of measurement that you make. You want to always make sure that you record units. The reason for that is pretty simple. If I wrote 200 down, really, who knows what I'm talking about? You know, I could have $200, which would be great. I could have 200 pennies, which would still be great, I think. But it could be like 200 degrees outside, which it feels like every day of the week these days. But, you know, we really do need to always have both a number and a unit, because the unit really does give us a frame of reference for really what the number represents. So I'll go with the modest pennies here. Now, it's important when we take measurements to always make sure that we do take measurements correctly. So let's take a look. So let's just say we have like a ruler here. Straightest ruler. There you go. We'll say those are some centimeters happening there. And let's say we wanted to take a measurement here. We'll go with this line here. So if we want to take a measurement of this line, and really, whenever you take a measurement, there's always some degree of uncertainty with a measurement. So there's always some degree of uncertainty when you take a measurement. The degree of uncertainty really does depend on sort of the piece of equipment that you're using. And every equipment is a little bit different, which is why you should always look at the piece of equipment you're using and really figure out how far you can take that measurement to. There's really kind of two markings on most pieces of equipment that we use that are important. One is the big markings, if you will, or the larger markings. And in this particular case, if we look at the big markings, the difference between the big markings is 1 centimeter. The other markings that we want to look at really are the smaller markings. And when we look at the smaller markings, what we want to do is basically count up how many of those smaller markings we have. And we typically start counting after the last large marking. So we would actually start counting here. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9. And we finish up on the next biggest marking is where we finish up. I hope I counted that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So in this particular case, we have 10 markings. The overall sort of value difference there, right, is 1 centimeter. That means each of the smallest markings represents how much? Represents 0.1 of a centimeter, right? This guy would be like 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, and so forth, all the way up there to 2 in this case. Now, when we do take a measurement, there is always certain numbers that pretty much, no matter who takes a look at it, everybody should agree. And I would hope everybody agrees that this arrow is at least 1.5. So we would want to always record those numbers. These are sometimes referred to as our certain numbers. Now, we could clearly see that our arrow here is not exactly at 1.5, and it's not really at 1.6. It is somewhere between those two numbers. And this is really where the estimation is going to come into play. So this is where, you know, I may look at it and go, I think it's just a little bit past halfway there. So maybe I want to record that last one as like a 7. And then obviously we would include our units. Somebody else may look at it and go, hey, I think it's like dead on center there. And we would record it maybe as a 5. So that's really where the uncertainty in this measurement is going to lie. And this is what is sometimes referred to as the first uncertain digit. And when you take a measurement, it is always custom to record all of the certain numbers and that very first uncertain number. And that is what everybody's favorite things are. Those are really what significant figures are. Which means this particular measurement would have how many significant figures? It would have 3 significant figures. All of them would be significant in this particular case, where the uncertainty lies in the very last digit, where, it could be a little bit higher than that. Maybe it's 1.58, maybe it's 1.56, but that is sort of where the uncertainty sort of lies in this particular measurement. Any questions on that? Now, you can figure out sort of the precision of a particular piece of equipment by taking the smaller units and basically dividing it by 2. So for example, if I took the smaller units here, which is 0.1 of a centimeter, and I divide it by 2, I am going to end up with something like 0.05 centimeters, plus or minus basically 0.05 centimeters. Let's come back. That is basically where we took our reading to, right? 2 decimal places. 2 decimal places is where we took our reading to. And that's really how far you can take it in this particular case. Speaking of that, there is a difference, right, between sort of accuracy, right, and precision. Those two things mean some different things, and we'll talk about it in just a second. But let's look at another example here. Let's look at clearly the quality control there at the plant was not so good there. But this is a wonderfully drawn graduated cylinder here. And let's put some liquid in there. Why not? We'll go there. Now, typically when we put liquid, like in a glass container, we typically will see the curvature of the liquid. Let me hyper exaggerate that. That is what is known as the meniscus, right? And you should always read from the bottom of the meniscus is typically where you should read. And that is because it is crawling up the sides of the wall, because the solution that's in there is actually more attracted to the wall than itself. So what ends up happening is the sides that are in contact start crawling up the wall, and it causes it to make the meniscus sort of shape. And that's why we read from the bottom of the meniscus, because the true volume is actually in the center there, because it's not affected by the walls of the container. It's not crawling up. That's actually where the volume actually is in that particular container. So if we look at this scale, we could kind of do the same thing. We could look at the major markings, 10 and 20. So our big markings in this case is 10 milliliters. Once again, if we count how many markings we got going on there, smaller markings, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings happening there. And that means that we have 10 markings where the difference between those is 10 milliliters. 10 divided by 10 is 1 milliliter. That means each of the smallest markings in this particular case is actually 1 milliliter. This would be 11-ish, 12, 13, 14, 15, 16, 17, 18, 19, and so forth. So if we were to look at my meniscus, we'll go right about there, we'll call it. And we were to take a reading, everybody that looks at it should see it is at least 15. So we would want to record 15 in this case. Those again would be our certain numbers. Once again, here it's not exactly 15, not exactly 16. So some type of estimate would have to be made at this point. And perhaps you go, I think it's kind of nearing the 15. Maybe we'll go with 3. Once again, we would put our units. That would be all of our certain numbers plus our first uncertain number. This guy would have, again, how many significant figures? Would have 3 significant figures. Where the uncertainty in this measurement would come right about there. And the last significant figure is where the uncertainty lies in that measurement. Again, saying basically it could be like 15.4, 15.2 in that ballpark, which is about what we see here. The sort of precision on this one, we could take our 1 milliliter divided by 2 gives us plus or minus 0.5 milliliters, which is the first decimal place, which is exactly where we took the reading to. In general, you could take the reading to typically one more place to the right of the smallest marking is typically where you could take that reading. Not all the time, but in most cases, you could go one more place to the right. To sort of give you an example of maybe a situation where you cannot do that, let's take the graduated cylinder that maybe looks like this. It is. So we got this. And we'll go put our liquid right about there. So in this case, our biggest markings, once again, going to be 10 milliliters. And if we count up our smaller markings here, we got 1, 2, 3, 4, and 5 markings happening here. In this case, each of the smallest markings represents how many milliliters? It does represent 2 milliliters. So the smallest markings here actually represents 2 milliliters. That would then make that 12, 14, 16, and 18 happening here. So now when we go look at our solution that's in this particular piece of equipment, we do find ourselves between basically 14 and 16. And the number that comes between 14 and 16 is 15 in this case. And that's really the best that you could do. This would be 15 milliliters. There's no good way to figure out where 14 ends, 15 starts in that little space between those numbers. So the best that you can do is actually take it to 15. This would have how many significant figures? It would have 2 significant figures. The uncertain number here would be the 5, right? It would be our uncertain number. So it could be like 14, could be 16. That's not the greatest measurement, right? There's a lot of sort of room for error in there. In this case, we could only take it to the 1s digit because of the piece of equipment, the way it's labeled. If you weren't sure how far you could take the reading, once again, you could just take the smallest markings divided by 2 gives you plus or minus 1 milliliter. And that's basically where you should take the reading in this particular case. Question on that there. Now, a very common mistake that people make when they take readings is this. We'll come back to this guy here. So let's say we had, go like right there. We'll go like dead on that sort of dash right there, right? So clearly this is the same setup. We have 1 centimeter as our big markings. We got 0.1 centimeter there as our smaller markings. What should we record here? Do we record 1.4 centimeters, 1.40 centimeters, or is there a difference between those 2 recordings? There is a difference between the 2 recordings, and let's take a look at what each of these differences would be. For example, here, if we look at this first one, this would have how many significant figures? It would have 2 significant figures, which means the uncertainty in this measurement would actually lie right there at the 4, which basically means you're saying, I think it's 1.4, but maybe it's like 1.5, maybe it's 1.3. And if you look at really this marking, it's really kind of nowhere near either of those sort of numbers, really, right? It's not even close. If we look at the bottom number, our measurement, that would have how many significant figures? It would have 3 significant figures. The uncertain number here would be the 0 in this case. And basically what you would be saying in that case is, I think it's 1.40 centimeters, but maybe it's like 1.41, maybe it's 1.39. And if you look at the marking, that's pretty much dead on about where it is and what we see with this piece of equipment. It is pretty much right about there. So what you should do is you definitely should record 1.40 in this particular case. If you record 1.4 and you lop off that number and that 0, you pretty much made your measurement pretty crappy. Yeah, you made it a lot worse of a measurement than it should have been based on the equipment that you have. There's a big room for error between 1.3 and 1.5 versus way over here, like 0.01 and 0.09 and stuff like that. So you never ever want to drop off a number. And that's why it's really important to make sure you look at the scale and you take the readings to the proper number of digits, because if you do get rid of something, you will be making your measurement a lot worse than it really should be. Any questions on measurements and how to take them? That being said, you should be taking proper measurements in lab for sure. We should be seeing units, everybody to the right number of digits. A couple other things about measurements. Typically speaking, if it is a digital display, like a scale or a balance, you usually record everything there that's digital, because it wouldn't probably be on the screen if it wasn't kind of important. Anything that is volumetric, which has really one type of marking, like a volumetric flask, a volumetric pipette. These are glasswares that basically have just one mark on it. That's usually it. They're also usually very expensive, so you don't want to break those things. But they usually have one mark. And anything that's volumetric, you typically do record to kind of 2 decimal places is typically where you take those sort of readings to. We talked about a second ago that, there is a difference between accuracy and precision. Right? Accuracy, or being accurate, is how close you are to the true value, while precision is how close really a group of values are to one another. So accuracy, or being accurate, means that whatever you did was pretty close to what you should have got, what the true value was. We look sometimes at accuracy by looking at what is referred to as percent error, is sometimes what we look at. So sometimes we look at percent error when we're looking at accuracy, and that is like your experimental value minus your true value divided by your true value times 100%. If you have a very low percent error, that means you did pretty good. You got pretty close to what you should have. If you have a really high percent error, that means you really kind of screwed up a lot. Yeah, you weren't very close to what you should have been. Precision, sometimes we look at standard deviation, percent standard deviation. And what we look at in terms of precision a lot of times in chemistry is why we do multiple trials, for example, of an experiment. We do multiple trials of an experiment to see if the experiment is reproducible, right? See if you get the same results every time you do the experiment. So we could look at something like precision to see how close each trial were to each other. Was the experiment sort of repeatable? It's like when we play bullseye, right? Throw some darts. The goal here is to hit the bullseye in the middle there. So if I take my darts and I throw it at the board, shoot one there, and sadly I missed the board completely. Hopefully nobody was standing there at that point. Am I very precise? I am not. Those guys are not really near each other, right? Am I very accurate? I am not either, because we're trying to get the bullseye in the middle. But it's been a long day, so I say, let's do a double or nothing and a friendly wager. Don't gamble. And let's also make the board much smaller as well. It makes it easier, maybe, or maybe it makes it harder. So I throw my darts a second time, and I go boom, boom, and boom. Am I precise? Am I accurate? No, I'm precisely not accurate in this case, right? Which brings up a really good point that, hey, you could absolutely do something the same way multiple times, and you could do it wrong every single time. You could be very good at doing something wrong the same way every single time. So it is possible to be very precise, right? But not very accurate. And like I said, maybe you misread the instructions, but you keep misreading the same spot and you keep doing the exact same thing. So you can be very, very precise and not very accurate, which is not necessarily usually when you're doing experiments. So why not? We go triple or nothing, because you always go triple or nothing, right? It's always a safe bet, I think. So I take my darts and I throw it again. And I hit right there. Am I accurate? Am I precise? Yes. So this is really the goal when you do experiments, right? You want to be very accurate of obviously trying to get whatever you're looking for, true values, but you also want to be very precise. You want to be able to repeat your experiments, right, and come up with the same results. And that's sort of the goal of what we're looking for. Any questions on that there? Okay. So now we talked about accuracy, precision. We touched upon significant figures. Let's do the official significant figure rollout here. So when we were counting significant figures, first off, any non-zero, right, is significant. So any non-zero number is going to be significant. So clearly, if I had something like 4, 5, 2, 5, we always start counting left to right. So we start right there. They are all non-zeros. They are all significant. This would have 4 significant figures in this particular case. Then we get to zeros, and those are usually the ones that give some people a hard time. Zeros. First type of zero is a leading zero, and those are not significant. So 0.000423. Once again, we start counting left to right. These are not significant. We do not start counting until we hit the very first non-zero, which happens to be the 4 in this case. The 2 and the 3 would also be significant. So this guy would have 3 significant figures. The 3 there at the end would be significant. Then we have some zeros that are trapped zeros or captive zeros. And those zeros are significant. And if we had something like 4007, starting counting here, that would be significant. These are trapped, which would make them significant. This number right here would also be significant. That gives us 4 significant figures in this particular case. Any question on those? Really, the troublesome zero, if you will, is usually this one right here, which is the trailing zero. The zeros that come at the end. And they may or may not be significant. What determines whether or not those zeros at the end are significant is if there is a decimal point anywhere in the number. Doesn't have to be near the zeros, but a decimal point anywhere in the number, they are significant. So if there is a, yes, there's a decimal point, then it is significant. So if I wrote 600 like this, and this was a measurement or something like that, how many significant figures would this have? That's a lot of numbers. People just keep yelling at me, but it actually would have just one, and it would be the 6. The zeros here at the end are not going to be significant in this case because there is no decimal point anywhere in that number, which means this has one significant figure. I go with 600.00. This would be significant. These are all zeros that now come at the end, and there is a decimal point right there, which would make them all significant. So this would be 5 significant figures is how many this guy would have. This number here, 0.00100300400, has how many significant figures? Well, I don't know. I just wrote the number. I just wasn't counting. I mean, all right, let's see. So we go left to right. These guys here are not going to be significant. Right about there is where we're going to start counting. These guys would be significant. That would be significant. They're still trapped. They're significant. Significant. Comes down to these two at the end. Are they significant? They are significant because way over here, there is a decimal point in there. I lost track. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures in this particular case. Any questions on that there? The uncertain digit in this number or measurement. Which one is the uncertain digit or estimated digit? It is the 2. Yes. And that's because that number, the way I wrote it, has 2 significant figures. And the estimated digit is not always the last number. A lot of times it is, but it is not always the last number. But what it is always the last significant figure. So because there's only 2 significant figures here, actually the 2 is this estimated digit. If I rewrote it like this, 12,000 with a little decimal, where would the estimated digit now become? It would be the 0. Yeah, the 0 would be your estimated digit. Which one's a much better measurement if these were measurements? The one on the right. Yeah, a lot less error there, right? First one's basically saying I think it's 12,000, but maybe it's 13, maybe it's 11,000. That's a pretty big spread, right? And all that kind of stuff. So that one is obviously these were measurements, a much first measurement. So it's important to keep in mind, sometimes people just go autopilot on that sort of question or that sort of thinking that it's always the last digit is always written, the last digit is always a sort of estimated digit, but it really is the last significant figure that's written is the estimated digit. Any questions on that there? Now, more importantly, there are 2 types of numbers. Ones are really measurements and significant figures, kind of like what we're doing here. And there's also numbers that are considered exact numbers, right? And exact numbers have really an unlimited number of significant figures. And when we do calculations that involve exact numbers, we really don't include them in our sort of calculations in terms of how many significant figures our answer should have. They're usually achieved 1 of 2 ways, either by counting or if it's some type of definition. Like 12 inches is 1 foot, something like that, some type of equality. Now, to understand exact numbers and sort of when you should use a definition as an exact number and when you should not, really revolves around the 2 different types of units that we have, right? And there are 2 types of units that we have are the English system, which we use here, and then pretty much everybody else, right, rolls with the metric system. So obviously that's an issue and has become an issue. And like 1960, they got together and came up with what we like to use a lot in chemistry and science, which is like the SI unit at the fun meeting known as the Conference of Weights and Measures in 1960. Sounds like a fun meeting. I'm sorry I missed it. But they came up with the SI unit, which is really, let's be honest, it's a metric version. of it, and it's really based off of the metric system. So why that's important is this: when you look at definitions that are English to English kind of conversion, like what I got up there, inches and feet, they're considered exact numbers. When you're going metric to metric sort of conversion, are using sort of an equality that's a metric to metric sort of relationship, they are also considered exact numbers. The one place, technically speaking, for most people sort of ignore it anyways in most cases, but when you cross over and kind of go English to metric, you really should look at the significant figures in the sort of conversion. It's the right way. Most people maybe don't do it all that often. And the reason they maybe don't do it all that often is it oftentimes will just default to the first number anyways in a lot of cases, but you really should look at it. There's a few places where you don't need to look at it, like everybody's favorite conversion of 1 inch is 2.54 centimeters, for example. That's an exact conversion. Some people will use 1 pound as 453.6 grams, also sort of an exact sort of conversion, but that's the one place really where you should kind of look at the sig figs if you're doing sort of a calculation to figure out, should you include them or not. If you overlook it in here, you'll probably be okay, but that's the one place really where you should kind of look at it. They're technically not considered sort of exact numbers, are not considered, they are considered exact numbers in that sense. All right. Speaking of that, let's talk about significant figures and calculations, which is really important. So when we're doing sig figs and calculations, really a couple of sort of processes we commonly do. We oftentimes will multiply maybe and divide, or we will add and subtract. Maybe we do both together. When we multiply and divide, the answer should have the same number of significant figures as the number with the least number of sig figs. So when we're multiplying or dividing, we're looking at significant figures of everybody involved. We're looking for the one with the smallest number of significant figures, and our answer should have the exact same number of significant figures as that. So if I took 423 and multiplied it by 12, that is 3 sig figs, that is 2 sig figs. My answer should end up with 2 significant figures when I multiply it. Same thing if I were doing some type of dividing as well. When we add and subtract, we're actually looking at decimal places here. And your answer should have the same number of decimal places as the number with the least number of decimal places. In each case, it really is the smallest or the least. And the reason for that is, frankly, that is your worst measurement. So you're only as good as sort of your worst measurement, like your weakest link, right? So it's the same idea. So if we were adding some numbers here, like 1.325 plus 2.1, I'm going to try it without the calculator. 5.2, that's a 4. I'm using my fingers there. 0.3. So 3.425. Here we would look at decimal places. That's 3 decimal places. That's 1 decimal place, which means we should take it to 1 decimal place, and that would give us an answer of 3.4. 3.4 has 1 decimal place, but how many significant figures? 2. So those are important things to keep a distinction of, in case you're going to go take that number and do something else with it, right? Any questions on calculations there? Now, clearly, if you are doing multiple sort of steps together, you should kind of keep track of everybody. So if you were doing something like 3.256 times 143 divided by 21, we were going to do this math, technically speaking, we would do the stuff in the parentheses up on top first. So we're multiplying. So this guy would be significant figures we're looking at, 4 significant figures. This guy would have 3 significant figures. That means technically speaking, when we get the answer up on top, should have about 3 significant figures. Then we're going to take the 3 significant figures and divide it by the guy on the bottom, which means we're still looking at significant figures. This guy would have 2 significant figures. That means my answer should end up with 2 significant figures along the way. You want to just keep track of your significant figures. Do you want to do a lot of rounding along the way if you're doing multiple steps? You don't, right? You want to wait to the very end to sort of clean it up. Some people teach you guard digits. Anyone? Good, because who cares about guard digits? But you want to keep a bunch of extra numbers that are there and kind of clean it up at the end. The reason you don't want to round, obviously, is every time you round, you're going to actually be moving yourself further and further away from the right answer, because it sort of compounds the problem every time you round if you continue on with that sort of calculation or that number in the calculation. Any questions on that there? Now, speaking of sort of numbers and calculations and keeping track of it, and we talked a little bit about rounding, you never want to do any kind of extreme rounding, right? You want to do just a normal rounding, which means if it's 5 or above, you're rounding up. If it's less than that, obviously you're just dropping the numbers off there. So for example, if I have 13,333 and I want to go to 2 significant figures, what would the answer be? Well, 2 significant figures takes me here, right? So we have 13. Any other answers? 13,000. Is there a difference? Yeah, I think there's a difference, right? Significant figure wise, is there a difference? There's not a difference significant figure wise. They're both 2, right? But there definitely is a difference in just a everyday example. Say I owed you $13,333. It's like an everyday example. And I say, hey, I'm just going to pay you 2 significant figures. Here's $13. Probably not making it out of the room, I'm assuming, in a friendly way. You're going to talk bad to me and say, hey, that's not right. That's what you're going to do to me. But maybe if I give you $13,000, you give me like the $333 teacher discount, like 20% off, maybe, depending on how the semester goes. I understand there's rules, but maybe you give me that discount. But more importantly here, we don't want to ever change the meaning of the number, right? So there is obviously a very big difference between 13 and like 13,000. So it happens a lot, and people sometimes are so focused in on obviously doing the right thing, which is giving the right number of significant figures, that they kind of do what I call extreme rounding. And there's like, that's all I see is significant figures. Forget about what the meanings of those numbers mean. So you want to always make sure you don't do anything crazy like that. Yeah. Any questions on that? Tough room. Can't even get the teacher discount in here. All right. So speaking of numbers, let's talk about other important things in terms of numbers, which is scientific notation. Yeah. Now, scientific notation is properly written in this form of n times 10 to the n, where the first n here is a number between 1 and 10. That means the number is not 10, 20, 100. That number there in the front is not like point something. It is a number between 1 and 10. This number here is obviously a number that can be positive or negative, really depending on which way you're moving. So if you got like 4, 5, 3, 2, and you want to turn it into scientific notation, we would go 1, 2, 3 places. Gives us 4.532 times 10 to the 3. We had this 0.00320. We would go 1, 2, 3 places to the right. Gives us 3.20 times 10 to the minus 3, I think. Couple important rules. First off, if it's a big number, it should have a positive exponent. If it's a smaller number, you'll have a negative exponent. And you should not lose any type of significant figures along the way. That is why I did not drop the 0 here. This has 3 significant figures written in scientific notation. This has 3 significant figures. That guy had 4 significant figures written in scientific notation. It has 4 significant figures, and that is because any part of a number, the front part that is written in scientific notation, those numbers are always significant. So that means sometimes the only way you could kind of hit the right number of significant figures is to write something in scientific notation, because you can basically control the number of significant figures that you have. So for example, if I needed 4 significant figures on this guy, I could just simply go 3.200 times 10 to the minus 3. I now have 4 significant figures. So always in scientific notation, all the numbers that come before the times 10 part are always significant. Any questions on that there? All right. Do you have to write every number in scientific notation? The answer is no. But you should give everybody to the right number of significant figures. So you could do that in decimal place, just as form as just as well as scientific notation. But as I mentioned, sometimes the only way to kind of get yourself to the right sig figs is scientific notation. Not so important the writing part of it, which it is, but more important is how to actually punch that into your calculator, because most people do not know how to properly punch that into your calculator. So let us talk about that here for a second, and the joy of calculators. On calculators, you do actually have exponent buttons. You will have an EE button. You may have an EXP button. And if you got one of those fancy two-tone calculators, you may actually have a button that looks like that. And if you usually have that button on that calculator, you usually got like a little wheel action going on there as well. So those are the major exponent buttons that are made by manufacturers these days. In addition, some other important buttons to look for on your calculator is the negative button, which is not the subtract button. So you usually have something like that, or maybe something like that as well. All right, so we'll talk about these two first. And if you have this, we'll talk about that in just a second, what you need to do on those type of calculators. So if you have a number that's in scientific notation, like you got 6.32 times 10 to the minus 6, and you want to actually punch that into your calculator, you absolutely positively should not use the multiplication button. You should absolutely positively not use the inverse log button. You should not use the caret or anything dumb like that, because you'll get the wrong answer eventually. You should actually use the exponent button, which is why they put it on that calculator and call it a scientific calculator, so you can use the actual button you should use. So if you were going to punch this in, you would go with 6.32. You would hit your exponent button. On a lot of calculators, what will happen is it will go 6.32, maybe pop an E there. You might get 6.32, pop up a couple of zeros, maybe a times 10 underneath there, depending on your calculator. But those are two commonly things that you will have. Now, when you do hit that exponent button, the EE button, the EXP button, it actually represents, when you hit this button, the times 10 part of the number, which is why I say you do not need to hit the multiplication button or anything like that. That actually takes care of the 10 times 10 part. What's left to punch into your calculator at this point is really the negative exponent. And once again, you do not want to use the subtract button. You do want to use your negative button there. And you then want to hit 6. That will give you a negative 6. That will turn this into like a negative 6. And that is the proper way to punch a number in scientific notation into your calculator. You should not be using any other buttons basically but those. Any questions on that there? Now, if you do have kind of that two-tone calculator, which is very commonly where you'll find the buttons there on the right, the only sort of difference that you have to do is, frankly, you got to put parentheses around every single number, because those calculators are typically programmed, I won't say wrong, but they're kind of programmed wrong, and they will do the math incorrectly. They will take your number that you want to put in scientific notation and like break it apart and do two separate kind of multiplication problems and stuff like that. So if you do have this button, you would start with actually a parentheses. You then would go 6.32. You would then hit your exponent button. And what will happen is you will actually have on your screen 6.32. It will pop the times 10 part, and you'll have your blinking cursor up there on top. At that point, you can actually put the rest of the number in. You could go with the negative button and then we've got there 6. And what that will then do is make it look something like this, times 10 to the minus 6. And now your blinking button cursor is still up on top, which you would think I could just close my parentheses at that point, but now your parentheses is going to be up on top like a superscript, and your calculator is going to yell at you like, what are you doing? That's not the right thing that you need to do. Hence the will. You go to your will and you hit the right-hand side there. That will bring your cursor back down where you could finally close your parentheses at this point, and then your calculator will be super happy with you and super proud of you that you just put that number in scientific notation correctly. So if you do have that type of calculator, it works perfectly fine. You just got to make sure that you really do parenthesis up everybody there. Otherwise, you will run into some problems. How do you know if you're really screwing up the calculation? Well, frankly, if you have the answer somewhere, that's a good answer that you don't have the same answer, but usually the front part of the number will look perfectly fine. So what I mean by that, let's just say that this was actually our answer. So usually this part of the number will be all good, but this part, the exponent part, is just slightly off. And usually if you're slightly off, it means you're probably punching into your calculator incorrectly. Any questions on that? It's super important to know how to use your calculator, especially for these first couple of chapters. There's a lot of numbers in scientific notation that you got to pop into your calculator, and you want to make sure that you do it correctly. If you're not sure where your button is or how to use it, just come see me. We'll figure it out together on your calculator. Why don't we try one here, just make sure everybody's calculator works okay. Let's go with 6.25 times 10 to the minus 6. We'll divide it by 1.2 times 10 to the 19. Why not? I'll do it as well since I just made it up. Okay, so hopefully you got some numbers on the screen, I hope. So let's take a look. So first off, let me just write how you should really properly put it in. Again, if you have the EE button or EXP button, if you have the other button, again, you just need to do the same thing, just put the parentheses like we talked about. You should go like 6.25. You should then hit your exponent button. You then have a negative exponent, which means you should hit the negative button and 6. Do a little divide button, 1.2 exponent button. This is actually a positive exponent, so you don't need the negative. So you just go 19 and hit it equals. Now I'm going to follow my suggestion there and do that. And let's see how we do. 6.25 exponent negative 6 divided by 1.2 exponent 19. You got a lot of numbers there, huh? So that is a 5.208333333 times 10 to the minus 25. That's a lot right there. First off, let's make sure we got that number. Did we get the number? Yes, hopefully. Okay. So clearly we should not ever give an answer like that, right? Because you don't really want to annoy me that much, right? And have the numbers wrap around the page or anything like that. We just did division, so we should look at what thing? Sig figs. First number has how many sig figs? Second number has, answer should have. First number is right here. Has 3 sig figs. This one has 2 sig figs, which means my answer should be right about there. So like a 5.2 times 10 to the minus 25, right? Would have 2 significant figures in this particular case. Again, if you have trouble with it, make sure you come see me and we'll figure it out on your particular calculator. More importantly, it's also a very common mistake that some people make, and maybe it's because maybe you rush through a calculation or something like that, is a lot of times they will kind of leave the times 10 part off and forget that part. They just see the big numbers on the calculator. And a lot of times, right, the times 10 part's like super squished at the very end. So you want to make sure that you don't forget that part of it. Also, that is the proper way and the way that you should write scientific notation. You should not write scientific notation like this. Even though it represents it, you should actually write it times 10 to the minus 25. All right, the most important part about scientific notation, make sure you know how to punch it into your calculator. You'll thank me when we start hitting those calculations very shortly in chapter 2. Any questions on that there? All right, so let's talk a little bit about also something, speaking of numbers, that people frankly screw up on. We talked about the metric system, and obviously in the metric system, we use a lot of prefixes, right, in that metric system. And sometimes you'll find a table where it says like 10 to the minus 1 is deci, 10 to the minus 2 is centi, kilo, I think, is 10 to the minus 10 to the 3, and so forth. And it's very much a common place that, well, frankly, people screw this up and go backwards on these conversions. So when you see a table like this, what you are seeing is how much there are in the base unit to one prefix unit. So when you say I have 1 kilogram, which is the prefix unit, that means you have 10 to the 3 grams, not the other way around. Not 10 to the 3 kilograms in 1 gram, which is, again, a super common error that a lot of people make. You got like 1 centimeter, that would be 10 to the minus 2 meters. Also, you could divide 10 to the minus 2 to the other side and have a whole number sort of conversion where 100 centimeters is basically 1 meter, right? So you could kind of do that. So again, it is a very common error that people make when they go use that table and that prefix table. They always get those guys sort of backwards. So whatever you see there is how much there is in the base unit being something like meters, liters, grams, whatever it may be, in one of the prefix unit. By the way, if you needed to punch that into your calculator, it's basically 1 times 10 to the 3, right? 1 times 10 to the minus 1. If you have typically a calculator that has that EE button, or go with the EE button, you actually could just hit the E and the minus 1 and it will do it correctly. Or you could just type it in as 1 times 10 to the minus 1, like we just talked about using scientific notation. Any question on the prefixes there? Okay, so the next thing is on our journey of remembrance here of all the fun stuff in the previous class is equalities, right? Qualities are 2 things that represent the same amount of something but are in different units, like our 12 inches is 1 foot. From any equality, you could write 2 conversion factors. You could say there are 12 inches in 1 foot, or in 1 foot, there are 12 inches. We do this because you should be doing your problems, and they should have taught you something known as dimensional analysis, which is a fancy way of saying I have unit A and I want to get rid of it. So to get rid of it, we go opposites. And I put unit A on the bottom and unit B up on top. We are multiplying on the top. We're dividing everybody on the bottom here. So unit A cancels each other out, gives us unit B that is here. So you should always show your work through dimensional analysis. You should always have the units. Otherwise, I'm just going to mark it wrong. Yes. All right. That's a good answer. So when we look at something like this, you would not use obviously both conversion factors. You would just use the one that will basically represent what you need. So obviously, if you had 22.5 feet and you want to know how many inches that was, you would do it like this: 22.5 feet. Opposite is 1 foot on the bottom, 12 inches up on top. These guys cancel. You take your handy dandy calculator, a little 22.5 times 12, gets you 270 inches, right? Significant figure wise, what am I looking at here? Should I look at this in terms of significant figures? The answer is no. It's an English to English conversion. So it's an exact number, which means you ignore it in a calculation. which means we would come back to this number, which is 3 significant figures. And did I write this correctly as 3 significant figures? I did not. It's actually 2 significant figures. There is no decimal point there. So if I did put a decimal point there, now I kind of did it right. Could also do it in scientific notation as 2.70 times 10 to the 2 inches, and it would be correct as well. So you should show all your work showing dimensional analysis with all the units, proper number of significant figures as you go through it. Now, if I had, say, something like, let's say we had 22.5 cubic feet. How many cubic centimeters would that be? So why don't you give that a try? So obviously there's 12 inches in a foot. And there is in 1 inch, 2.54 centimeters. Why don't you give that a go, see what you come up with. Cubic feet to cubic centimeters there. By the way, cubic centimeters, cubic feet, what type of measurement is that? Those are volumes, right? So if you take a length measurement like centimeters or something like that and you cube it, it becomes a volume, right? Speaking of which, right, a cubic centimeter is the same as a milliliter, right? And there's 1,000 milliliters in a liter. So we would start with our 22.5 cubic feet, and we actually want to do the conversion between feet to inches, perhaps. So 1 foot is 12 inches. Will this completely cancel everything out? It will not. This will only take care of one of them, right? So technically speaking, you got to do it like 3 times, right? If you really want to draw it out here. All right. 1 foot, 2 foot, 3 feet takes care of our cubic feet. If I stop right here and multiply it across the top, I got inches times inches times inches, which is cubic inches, which means I now need to go from inches to centimeters. And once again, I need to do it actually 3 times. And here we want to go opposite. So inches on the bottom, 1 inch is 2.54 centimeters. And once again, you do need to do it actually 3 times. 1 inch, 2 inches, 3 inches gives us cubic inches, takes care of all 3 of those, leaves me centimeters times centimeters times centimeters. We're going to multiply everything across the top, come back and divide by the bottom, which there's not much to divide by since it's all 1. Times 12, times 12, times 12, times 2.54. And you should end up with something. Let's see. We'll go with 6.37 times 10 to the 5th cubic centimeters. I went with 3 significant figures. Why? The original number was 3, and pretty much everything in the middle there, exact numbers, right? You don't have to worry about it. That's what I was saying earlier. For the most part, if you're unsure, you can probably make a pretty safe bet. If all you're doing is a conversion, however many sig figs that first number has, go with it for your answer. You'll probably be fairly close, if not right, most of the time. Not all the time. Now, can you do this in a shorter way by doing this move? I'm assuming, yeah, because I'm writing it. So I'm assuming you could do it that way, right? Would I do it this way? Well, I probably would, because I would probably make sure I actually did the math. Most people don't do the math, by the way. They put the cube up there and they just multiply by 12 once. Yeah. So maybe it's better to do it the other way. So you visually see, hey, you should probably do it 3 times. I can't tell you how many times people never, ever actually multiply that. Even though I kind of wrote the same conversion twice, that really should have been 2.54 centimeters is 1 inch there. There you go. But most people oftentimes will forget to actually do it 3 times. So if it visually helps you spread it out. If not, remember to do it correctly 3 times. Question on those type of volume, say cubic conversions. By the way, dimensional analysis, again, this is how you should show it. And if you do have sort of a number of conversions, you absolutely could do it all in one move, right? You could go from one unit to the next and show it that way. If you're more comfortable, you could do one conversion, get an answer, take it, do the next conversion, get an answer, take it, do the next conversion, get an answer. As we talked about earlier, you do just want to avoid rounding a lot in between each of the steps. If you kind of do it in steps, you want to make sure you don't round too much. Question on that? Our dimensional analysis or how to show it. Now, oftentimes we also will sometimes get percentages like 15.5% by mass. Sodium chloride. What is the best way to turn a percentage into like a usable type number is to assume you have how much of it? Assume you have 100, like your exam, right? You get like an 80% on your exam. You probably got 80 out of 100, right? You got 90 on your exam. Got 90 out of 100. You can assume as much as you want, but the numbers change. But if you assume 100, it stays the same. And if we did something like this, that would mean we had like 15.5 grams of sodium chloride in like 100 grams of solution, for example, or 100 grams of solution. We got 15.5 grams of sodium chloride. This was by mass, barely mass percent. So a lot of times we are given things in percentages, and an easy way to kind of convert it out is to do that. Question on conversions, dimensional analysis, how to do that. Everybody knows how to do it, I hope. Yes. Okay. Then we will finish our conversation here with the last favorite thing of everybody, which is density, right? Density is mass over volume, right? Common units of density for solids are grams per milliliter, are grams per cubic centimeter for solids and liquids. As I mentioned a second ago, a milliliter is the same thing as a cubic centimeter, also the same thing as a cc, right? Cc is a cubic centimeter. You hear it a lot in medical shows, like give the guy 5 cc's before he croaks, right? He's in higher need, you're giving him like 5 milliliters or what it is. What's that? Yeah, that's what it means. I had a girl that was from England, and they use cc a lot, and she would always say like 5 cc's of this, 5 cc's of that. I'm like, oh yeah. It took me a while to like, okay, I was never talking about. So those are all equal to each other. Those are common units. As we will see when we get to the gas chapter, gases are actually a lot of times given in grams per liter as a units of density when we do it. Density obviously has a formula, but if something is more dense than water, what happens? Sinks, yes. Something is less dense than water, it will float, right? If I take a Diet Coke can and a regular Coke can and put it into a sink of water, will they both float or they both sink? It's a good party trick. Yeah. One will sink, one will float. Yes, which one will float? Yes, the question was, if I put a Diet Coke can and a regular Coke can in a sink of water, which one will float? Yeah, the Diet Coke will float because it has artificial sweetener, right? Regular Coke has regular sugar, heavier, sinks to the bottom. Good trick. Also, open up a thing of 7-Up and put some raisins in a glass. The raisins start to bounce around because of the bubbles, right? I know, home thing, in case it's a long weekend, you never know. It's happening. These are things you got to know, I think. So density is mass divided by volume, which means we should be able to rearrange this correctly. Volume would be mass divided by density, and mass would be volume times density. Some people enjoy the DMV a lot, and that is the DMV triangle, we like to call it in the business. Mass is density times volume. Density is mass divided by volume. Volume is mass divided by density. Obviously, the units do not cancel when you calculate density. That's why you end up with mass over volume, they both stay in terms of the units. Number always stays with grams, always like 1 milliliter or cubic centimeter on the bottom. Oftentimes when we calculate density, there's a couple different ways we could get to the volume aspect of it. We can, as we did earlier today, simply take a reading of the volume. We could also, if we have some type of cube, measure the length times the width times the height. Those are all length measurements, but as we just talked about a second ago, if you take 3 length measurements and you multiply them together, that is how you get your cubic centimeters, which is a volume. And the very last way, which is the most common way that we get volume with density, is if you fill a container with some water or some type of liquid, and it has an initial volume, and I take something that is a solid and put it into that container, the volume level will go up or down. The volume will go up, right? In the container. The volume of liquid will be displaced, will be equal to the volume of the object you dump in there. And you can find the volume of that container by taking the difference there. So the volume of the object would be the final volume minus the initial volume. And that's a very common way, called volume by displacement, is how you would figure that out. Any questions on density? Any questions on the pre stuff? Actually, wait, one more pre stuff. Hang on. I felt like I was done. I felt like I got one more in me. All right. Thank you. I appreciate the encouragement. Temperature, to make sure we're all on the same temperature page here today. It's hot outside. That was your temperature report. All right. There are 3 scales. There's degrees Fahrenheit. It's Thursday. All right. It's the end of the week. Give a guy a break. All right. Degrees Fahrenheit, degrees Celsius, and our favorite, which is Kelvin, right? First off, we obviously do not use degrees Kelvin. It's just Kelvin. The differences between these is really based on where the freezing and boiling point of water is on each of these scales. And to convert to Kelvin from Celsius, to go from degrees Celsius to Kelvin, which is pretty much all we do in chemistry, is get our temperature into Kelvin. Pretty much every equation, if it is a temperature and you want to do it right, you should do it in Kelvin. The only exception would be like specific heat. We leave that in Celsius a lot, but the reason we do this conversion a lot is our thermometers are in Celsius. So we oftentimes have to convert from Celsius to Kelvin. So that's going to be the temperature in Kelvin is equal to the temperature in Celsius plus a 273. That also means if you got to go the other way, temperature in Celsius would be a temperature in Kelvin minus a 273. Might answer your question. The real number is 273.15. Was that your question? All right. So the real numbers, I know, you see, I work in the circus, mind readers, part-time job in case the teaching thing doesn't work out. So the 273, what's that? Most people round off the 0.15, but if you're a fan of the 0.15, you could keep it. You're going to round it off anyways, but if you want to leave it, you can. But 273 is what most people would do. If you're going from degrees Celsius to Fahrenheit, which would be not very often in chemistry, the temperature in Fahrenheit is equal to 1.8, the temperature in Celsius plus a 32. If you want to go from degrees Fahrenheit to Celsius, it is the temperature in Fahrenheit minus 32 divided by 1.80. The 1.80 is the difference between 180 units difference between freezing and boiling on the temperature scale. It's also the same thing as 9/5, which you might have learned when you were younger. It all works the same. There is a special rule that people use when you're doing nothing more than a temperature conversion in significant figures. And the rule is, if all you're doing is changing the temperature scale and doing that conversion, you basically make the converted number look like the original number. So if your original number was like 301.5 Kelvin and you wanted to take it to degrees Celsius, you would take it to 1 decimal place your answer. If your original guy was like 41 degrees Celsius and you wanted to go to degrees Fahrenheit, you would take it to a whole number once you're done converting. The reason for that is some people use 1.8, some people use 1.80, some people use 9/5. So there's a lot of variations in sort of the formulas to do the conversions. So most people follow the general rule of whatever the original temperature number looked like, whole number, first decimal place, 2 decimal places, you take the converted number to look the same. I would say after all these guys here, these are really the 2 that you would use the most. And I would say that that definitely is the one that you would probably use the most in chemistry. And obviously it will not be provided for you. So you do need to know it, either 273 or 273.15. Well, I feel good about it. I don't know how you feel.